In this video, we're going to discuss some of the fundamentals in terms of chemistry calculations. So a new concept that we call moles, Avogadro's number, converting from moles to grams, grams to moles, mass to mass conversions, that sort of thing. So Avogadro's number, which I've mentioned before, it's just a number. So this is its numerical value. And I say it's just a number, just like when we say a dozen just means 12, and a baker's dozen means 13. Avogadro's number is 6.022 times 10 to the 23rd. And this number would be it's given on equation sheets anytime you take chemistry exams, just as a general rule, but you'll end up memorizing this, and you should try to memorize it if you can. But it's defined as the number of atoms in 12.01 grams of carbon, and it's 12.01 because that's the molar mass of carbon. So carbon has been used as our baseline to try and, pinpoint exactly how much or how many things or atoms are in 1 mole. We use carbon as our baseline. So 12.01 grams of carbon has 6.022 times 10 to the 23 carbon atoms. This is kind of like a definition that we use to establish the value of Avogadro's number. Now, 1 mole, so abbreviated as a unit, it's MOL, the whole word, MOLE. It's a unit of measure for the amount of a chemical substance. And we use this because we're talking about atoms, molecules, extremely small things, whereas a mole of a substance is something much more tangible and manageable. Like a mole of copper could fit in the palm of your hand, and it's macroscopic. You can actually see it. That's why we use a mole. So if we say a mole is basically equivalent to Avogadro's number. So if we say we have 1 mole of atoms, then we have 6.022 times 10 to the 23rd atoms. So 1 mole is pretty much defined to be 6.022 times 10 to the 23. And they say units because it could be anything. It could be atoms, molecules, grains of sand, whatever. 1 mole, 1 Avogadro's number is 6.022 times 10 to the 23rd, just like 1 dozen is 12, and 1 gross is 144, I believe. 1 mole is 6.022 times 10 to the 23rd. So we can use, and we will, use mole relationships to convert between the number of particles and the mass of a substance. We will use this regularly throughout the rest of the course, converting between moles and grams and moles. So for example, how many sodium atoms are in 0.24 moles of sodium? So they're asking how many sodium atoms, so we want atoms of sodium. We know that we have 0.24 moles of sodium, and then this is our conversion, 6.022 times 10 to the 23rd. So this is how we would set this up. If we wanted to convert from moles to atoms, we start off with our 0.24 moles of sodium. This is our conversion factor, what they might call the unit factor, or basically just our conversion. Now, they've got this mole of sodium and mole of sodium with the red line crossed out because anytime we set up units like this, we want to make sure we're showing our units canceling. So we have moles of sodium here, and then we put moles of sodium in the denominator so that we can show it canceling. And then 1 mole is defined as 6.022 times 10 to the 23rd atoms. So that's why that's on top. So 6.022 times 10 to the 23rd atoms is the same thing as 1 mole of sodium. And then our units cancel, and then we're left, in terms of units, atoms of sodium. And then this is just what our calculator tells us. I suggest you practice. Go ahead and type in 0.24 times 6.022 times 10 to the 23rd, and make sure you can get the same value, because that is just making sure that you can do the calculation successfully and correctly on your calculator. So another example, how many moles of aluminum are in 3.42 times 10 to the 21st atoms of aluminum? So we want to calculate moles. That's what they asked for, how many moles. We're given 3.42 times 10 to the 21st atoms of aluminum, and this is our conversion factor. So we start off with 3.42 times 10 to the 21st atoms. Atoms is the units that we want to cancel, so that's why we put the atoms on the bottom here so that our units could cancel. And by definition, 6.022 times 10 to the 23rd is equal to 1 mole. And then in terms of units, We have moles of aluminum as our unit, so here's our units, moles of aluminum, and this is the value that your calculator should tell you if you type everything in correctly, which again, I recommend you try. Take this value, divide it by this value, and make sure that you can indeed get your calculator to output that value, because that is practice using your calculator correctly. So the next thing is very important, the molar mass of a substance. It has units of grams per mole, but it's essentially the atomic mass of any substance. We use molar mass. It's basically how many grams 1 mole of that substance would weigh. Now, AMU is another way of expressing molar mass, and then in biology, you'd also see Daltons, but grams per mole is what we're going to use for the most part. But molar mass of carbon is 12 grams per mole, and the molar mass of any substance on the periodic table, it's that decimal number that you see. So for example, nitrogen on ptable.com, it says 14.007 grams per mole. And fluorine, or actually I'll do chlorine as an example. Chlorine is 35.45 grams per mole. But that's saying that if you had 1 mole of chlorine, it would weigh 35.45 grams. Now, one important thing about our diatomics, so like nitrogen, for example, it's one of the 7 diatomics. So if you actually had a mole of nitrogen gas, then you're going to want to double the value that you see on the periodic table. If you're talking about a mole of nitrogen atoms, then it's just the value that's on the periodic table. But if you're talking about the diatomic gas, then you'd want to double it, so 28 instead of 14. But yeah, those 7 diatomics, make sure you have those memorized as well, because that's when it could also come up. That's when they're another way that they're important. So then the molar mass of a substance, we were just doing atoms, but if we actually had a substance, it's just the sum of all the molar masses of each individual element. So we have copper 2 nitrate as an example. So here's our copper, here's our nitrate. If we wanted to find the molar mass of copper 2 nitrate, we pretty much sum the atomic masses of all of the individual elements. So 63.55, that is the value for copper off the periodic table. Now we've got this 2 right here for this 2 because there's 2 nitrites in the formula. This 14 is for the nitrogen. This 16, or both of these 16s, are for the oxygens. But you pretty much just add them all up, and we get 155.57 grams per mole for the molar mass of copper 2 nitrite. So next, if we want to do the molar mass of a compound and use that to convert between grams and moles, we're going to use the molar mass essentially. So if we said, if for a substance, how many grams is 1 mole of copper 2 nitrate, we're going to use the molar mass to do this conversion. And then same thing, if we want to do, if we're going to do particles to mass, we're going to use Avogadros number. If we're going to go grams to moles or moles to grams, we're going to use the molar mass. If we're going to go from grams to moles to atoms, that's going to require 2 steps, but we'll do a few examples of each one. So here's another example. So what is the mass of 1.33 moles of titanium? So step 1, it said we want grams. They said, what is the mass? That means they're asking for grams. We're given 1.33 moles of titanium. And we're going to need the molar mass of titanium, and this 47.88, that came directly from the periodic table. So ptable.com says 47.867, 47.88, close enough. So this is our setup. So we start off with what was given, 1.33 moles of titanium. This is the molar mass of titanium off the periodic table, and it's grams per mole. So it's 47.88 grams per 1 mole. That's what the grams per mole means, is it's grams per 1 mole. Since we want moles to cancel, we put the moles part of this on the bottom and the grams part of it on the top. And then in our calculators, we do 1.33 times 47.88. Verify that you get the same answer when you do the calculation on your calculator. Another example. So what is the mass of 2.55 times 10 to the 23 atoms of lead? So we're going to require 2 conversions this time, because we need to go from atoms to moles and then moles to grams in order to get the mass of this amount of lead. So we want grams. So that's why we have grams over here. We're starting off with atoms, so we have the atoms part over here. And then we're going to have two conversions, so Avogadro's number and the molar mass. So first we're going to use Avogadro's number, and then we're going to use molar mass. So the Avogadro's number we use because we need to cancel the atoms part of it. And it is, by definition, 6.022 times 10 to the 23rd atoms per mole. So that's why we put atoms in the denominator and moles in the top. And then with the second conversion, molar masses are always grams per mole. And this 207.2 number, that came directly off the periodic table. So you find lead from the periodic table, it's element number 82. ptable.com says 207.2, so exactly what the slide has. It's 207.2 grams per 1 mole. We put the mole part on the bottom so that the units could cancel with what we had over here. And then just in terms of units, atoms canceled, moles canceled, we're left with grams, which is what we wanted. Again, this 87.9, verify that you can get the same answer on your calculator. So this number divided by Avogadro's number times the molar mass of lead, you should get 87.9. Make sure you can reproduce that answer on your calculator. So now an example of mass to molecules. So how many fluorine molecules are present in 2.25 grams of fluorine gas? So careful, we have a diatomic here that's going to affect the molar mass that we use in our calculation. So we want molecules, and here this should say F2. We want molecules of F2, and we're starting off with grams. So we start off with our 2.25 grams of diatomic fluorine. So we're going to use the molar mass and Avogadro's number to do this conversion. So the molar mass, notice it says 38 because we're talking about diatomic fluorine. So from the periodic table, looking at ptable.com, fluorine says 18.998. So if you multiply that by 2 because it's diatomic fluorine, 18.998 times 2 is about 38, which is why they have 38 grams per mole right here for the molar mass. So that takes care of grams of fluorine in terms of canceling units. Next, we want to cancel the moles of fluorine, so we're going to use Avogadro's number, which is by definition 6.022 times 10 to the 23rd things per mole, so molecules in this case. So moles of fluorine is going to cancel, and we're left with molecules for our units. Here's your answer, and again, just verify that you can get the same answer on your calculator. Sometimes with calculators, you have to use parentheses just to make sure it all comes out properly, but 2.25 divided by 38 times Avogadro's number, you should get this quantity if you're doing things correctly on your calculator. So mass of a single atom or molecule, this is not something we do very often, but it is something we could calculate. So here's a question, says, what is the mass of a single molecule of sulfur dioxide? They give us the molar mass. Now keep in mind, molar mass, this is the mass per mole of molecules, but this problem is saying, what's the mass of just a single molecule? So we're going to have to use Avogadro's number to get down to the mass of just a single molecule. So we're going to start off with the molar mass, 64.07 grams for an entire mole of sulfur dioxide. And then if we use Avogadro's number to cancel the moles part of it, now our units will be grams per molecule. So that's why we have grams per molecule written here. And then we'll get some really tiny numbers. So 10 to the negative 22, that's a really, really small number. And that makes sense because molecules are super tiny. Molecules should have a very, very small mass. But again, just double check that you can indeed reproduce this answer on your calculator, because if you can, that means you're probably using your calculator correctly, which is an important skill in chemistry or any science class naturally. So next up, interpreting chemical equations. So here's an example that we're going to look at. So we've got nitrogen monoxide with oxygen producing nitrogen dioxide. So this UV over here, when we talked about chemical reactions, anything that's written over the arrow, that's going to be kind of like a catalyst. So in this example, it's kind of like the catalyst is UV light from the sun. But here, what we're actually trying to say is happening in this reaction is we have two nitrogen monoxide molecules, so that's why I've drawn it twice over here, reacting with one diatomic oxygen. and then it produces 2 of the NO2s. So here's our 2 NO2 molecules. 2 molecules of NO gas react with 1 molecule of O2 gas to produce 2 molecules of NO2 gas. So this gets into the coefficients, and then here's the coefficient of 1, which is why we have 1 molecule here. But you need to be able to interpret a chemical reaction appropriately if you're going to do any sort of conversions using the reaction. So if you wanted to, for example, convert between grams of nitrogen monoxide to grams of nitrogen dioxide, you need to be able to balance the reactions correctly and get these coefficients, because we're going to use these for the next part when we're doing more conversions. So we're still on the topic of conversions, it's just now we're going to do it with the use of a chemical equation. So the coefficients are representing the whole molecules. Again, here's a 1, here's another number 2. So if we want to kind of illustrate exactly what's happening, we could say we've got 2 molecules reacting with 1 molecule to make 2 molecules. That's equivalent to saying we had 2,000 or 1,000 or 2,000. So these are all the ratios that are staying constant. 12.04, that's basically Avogadro's number times 2. Then the 1 mole of O2 and then 2 moles of NO2. This is the most common way that we'll just colloquially talk about it. 2 moles of NO react with 1 mole of O2 to make 2 moles of NO2, which is why they have 2 moles here, 1 mole here, and 2 moles here. The point is the ratio is what's important. So anytime they're talking about like what's the molar ratio, let me write that down. Molar ratio. If we said what's the molar ratio between nitrogen monoxide and oxygen gas, it's a 2-to-1 ratio. And it's the ratio that's important for when you're going to do conversions like moles to grams, so like or grams to grams, like grams of NO to grams of oxygen. You're going to need that molar ratio to go between 2 different substances, which is, we weren't doing that in the previous slides. We're going to be doing that next. So we can read the above. We can basically, if we wanted to read this reaction as a sentence, we could say 2 moles of NO gas react with 1 mole of O2 gas to produce 2 moles of NO2 gas. This is how we will speak reactions. If we had to put this reaction as a sentence, this is how we would say it. 2 moles of NO gas react with 1 mole of oxygen gas to make 2 moles of nitrogen dioxide gas. And then these coefficients indicate the mole ratio, which is really, really important for doing conversions between substances. So for a balanced chemical equation, we know how many molecules or moles are going to react and how many moles of product are produced. And we can also use it, we're not going to do it in this lecture, but we can also do this in terms of liters. So we can go from liters of one substance to liters of another for gases. But we're just going to stick with moles for right now. Working with liters is like the second half of chapters 8 and 9, which we're going to do separately. So law of conservation of mass, which we've kind of already gone over, but it basically states that mass is neither created nor destroyed. So using this same example, if we had, following the same molar ratios, 2 to 1 to 2, if we insert the molar mass of each one, so this 30.01, that's the molar mass of nitrogen monoxide, which again you get just by adding up 14 for nitrogen plus 16 for oxygen, you'll get about 30. And then here's the molar mass for diatomic oxygen, and here's the molar mass for nitrogen dioxide. Just checking the math, we get 92 equals 92, so that's just basically confirming the law of conservation of mass. So mass is neither created nor destroyed. The mass of the reactants is equal to the mass of the products. Mass is indeed conserved if we're assuming we start with 2 moles and 1 mole, just like the mole ratios have. So now with these mole ratios, we can convert between one substance to another. That's the entire point of the mole ratios. These are all the different mole ratios that you could accurately write. So with this new example, nitrogen plus oxygen makes nitrogen monoxide. This is a 1, and this is a 1, and then this one we have a 2. So between nitrogen and oxygen, we have a 1-to-1 ratio. Between nitrogen and nitrogen monoxide, it's a 1 to 2 or 2 to 1 ratio, depending on which direction you're going, so to speak. And same thing for between oxygen and nitrogen monoxide. It's a 1 to 2, 2 to 1 ratio. This should be a 2 right here. These slides are just full of typos. Now, Here, we're going to actually use the mole to mole ratio to do a conversion. So here it's saying like how many moles of oxygen react when we have 2.25 moles of nitrogen. So you have 2.25 moles of nitrogen, how many moles of oxygen gas are going to be needed to react? So using the same kind of setups as the earlier reactions, we want moles of oxygen and we're given moles of nitrogen. And here's our mole ratio. And this 1-to-1 mole ratio came from the balanced chemical equation. It's just the coefficients, those numbers written in front. And we're going to use that basically as a conversion factor right here. So this is our mole ratio conversion factor. Starting off with 2.25 moles of nitrogen, and we want to calculate moles of oxygen. Now, in terms of how the ratio is set up, now it's trivial in this case because it's just 1/1. But in terms of units, which it's really important to show your units, especially on a quiz or a test, and even like an in-person quiz or a test, but on the test that you're going to have, it's really important to show your units. So I put moles of N2 on the bottom because that's what I need to cancel. I started with moles of N2. I want to cancel moles of N2, and I want to get moles of oxygen. So this 1-to-1 mole ratio has my unit set up with moles of oxygen on the top and moles of nitrogen on the bottom. And then obviously we're still going to get 2.25 because 2.25 times 1 divided by 1 is still 2.25. Now, all of this process using the units to calculate stuff and then the mole ratios, this is all called stoichiometry. So chemists and chemical engineers perform these calculations all the time based on balanced chemical reactions to predict like how much we'll make, predict how much we need. So in the real world, we'll use this to predict the cost of doing chemical reactions. We can predict how many kilograms of something we need and how much does that cost, how much should we order, that sort of thing. But these calculations are often used to avoid large excess amounts in terms of the reactants, or calculate how much product are you going to make. Oh, I'm going to make too much. Maybe I should scale my reaction back, or I'm not going to make enough. I need to double my reactants. All of this is called stoichiometry. Stoichiometry is basically using the mole ratios, the mole-to-mole relationships in chemical reactions to go between substances. Again, it's pronounced stoichiometry. So we're going to basically use stoichiometry to go between substances, going from grams to grams. We can also go from grams to liters if we're talking about gases, or going from liters to liters if we have something that's all gases. Now, these two we're not going to do in this video. We're just going to focus on this one for right now, but it's all the same thing. It's all stoichiometry. So in mass-to-mass stoichiometry problems, which is what we're going to focus on for the rest of this video, or at least just this video, we're not going to do volume yet. We're going to use a given mass of reactant or product and eventually convert that to mass of something else, mass of a different substance. Now we cannot simply just go from grams to grams. We must first go from grams to moles to grams. And if we're converting from like substance A to substance B, it's grams of A to moles of A to moles of B, and then to grams of B. So we cannot just go from grams to grams. You cannot do that. So basically, we're going to start off with the given mass of substance converting to moles using the molar mass. Then we're going to go from moles of one substance to moles of the other using the coefficients, so using the molar ratios. Then we go from moles of the second substance into grams using the molar mass of that substance. So that means first we'd use molar mass of A, and then we'd use the molar ratio in the middle, and then we'd use the molar mass of B. That's the basic strategy anytime you have a mass-to-mass stoichiometry problem. So here's an example. We have mass to say, what is the mass of mercury produced from the decomposition of 1.25 grams of mercury 2 oxide? And they give us the molar mass, which is quite nice. Very, very kind of them to do that. So we're going to go, we want to get grams of mercury, and we're starting with 1.25 grams of the mercury 2 oxide. So the first thing we would do, we're starting, this is the molar mass of mercury, so this is actually the last step. They've kind of got this written backwards, but we're going to be starting off, here they've got written properly, so I'm going to skip this slide because I feel like they phrased it backwards. Here it's more correct. So we've got the 1.25 grams of mercury 2 oxide, which is what we started off with. and then they gave us the molar mass for that mercury oxide, so that's what we're using here. Now with the balanced chemical equation, which if they don't give you the equation balanced, you need to balance it yourself, but it's just generally a good strategy to double check that everything is already balanced. Now this one, they wrote this backwards. This is mercury oxide, this should be mercury, and this should be mercury. But this is our basic strategy that I was outlining on the previous slide. So we're starting off with grams of mercury oxide, which is right here. And then we're going to use the molar mass of the mercury oxide, which they gave to us. Then we're going to use the molar ratio, which they both have 2's in front. So it's just a 2 to 2 mole ratio. And then this is the molar mass of mercury. So in terms of units, the molar mass the first time was written with grams on the bottom so that grams of mercury oxide could cancel. Then with the mole ratio, the mercury was on top and the mercury 2 oxide on the bottom so that moles of mercury oxide could cancel. And then with the second use of molar mass of mercury, we put moles on the bottom so that moles of mercury could cancel. And you should get 1.16. Just verify that this is the answer you get typing these things in. So 1.25 divided by 216. This is pretty much just 1 because it's 2 divided by 2 is 1, and then times 200. You should get a value close to that.